Hello and welcome to this video for Chemistry 30. We are going to be looking at calculating pH for acids today. The next video is going to look at calculating for bases. Now, when you're doing your calculation for acids, it depends on whether you have a strong acid or a weak acid as to its conductivity, its pH level, as well as how quickly it reacts with other substances. Primarily, acids react with metals to produce hydrogen gas bubbles in a solution. So that'll happen more rapidly if it's a strong acid. Now, when it comes to whether or not you have a strong acid or base, this is the data booklet chart that students in Alberta get for Chemistry 30. And everything written above the hydronium ion are your strong acids. There's 6 of them. They are the strong acids, okay? Every other acid on this chart written below are therefore weak acids, all right? Now notice how there's a value written here, Ka. It tells you that Ka is very large for strong acids, and then for the weak acids, there's actual a value to it. And that's what we're going to use today when we calculate the pH of a weak acid. Okay? The pH of a strong acid is actually very straightforward. A strong acid 100% ionizes. So that means that the concentration of the hydronium ion will 100% be coming from the acid. Okay, so if you are asked to calculate the pH and you identify that you have a strong acid, so HNO3 is obviously an acid. It has a donatable hydrogen in it. And then you check the data booklet. It's one of the top 6 strong acids. So because it's a strong acid, that means the concentration of the hydronium ion is the concentration of the acid. So all we have to do is take the negative log then of that concentration given in the question, and that's going to give us pH. Remember, for pH, your sig digs are total digits in concentration have to equal decimal places in pH. Okay, so the answer to this question would be 0.301. So very straightforward. The concentration of the hydronium ion is the concentration of the acid if you have, again, a strong acid. And the strong acids, again, in the data booklet are the top 6. Or you could be given another acid. As long as the Ka of the acid is greater than 1, it is a strong acid, okay? And what I mention here as well is that at equilibrium, you have a greater concentration of products than reactants. So the products, again, when I'm talking about an acid in water, the acid is donating its hydrogen to water to produce the hydronium ion and the anion, okay? So those ions are in greatest concentration at equilibrium because all of the reactant, the acid essentially, is gone, fully making the ions. Okay? Now, what do we do when we have a weak acid? Weak acids are not ionizing all the way. They're actually only ionizing partly, usually less than 50%. So that means that it is reactant favored. There is more acid present than the hydronium ions that it is ionizing into. So to calculate the pH, we're actually going to be using those Ka values that are in the data booklet to help us find the concentration of the hydronium ion because it will not be the concentration of the weak acid. It's not 100% ionizing. So if we look at our equilibrium reaction again of an acid is going to, again, react with water, transferring its hydrogen to the water to make the hydronium ion and the anion. Now, if I were to do an ice table for this, because essentially that's what we need to do, is we need to find what is the equilibrium concentration of the hydronium ion. That is what we are looking for. So I would have an initial concentration of my acid. The water wouldn't be included in the equilibrium expression, so we don't need to include it in our ice table. My hydronium ion concentration before the acid's placed in water, we assume is 0, and the anion is 0. So the acid is going to go down by 1x, and the products are both going to go up by 1x because they have a balancing coefficient of 1. The number of x changes that it goes through is based on its balancing coefficient. So at equilibrium, I'll have my acid concentration minus x, and my two products will both be x. So if I put that into my Ka formula, it would be x squared over, and again, it's x squared. If I actually will put it like this first, it's x times x, which simplifies into x squared, over the concentration of the acid minus x. Now, your Ka values are all going to be very small, which means we can use our approximation method and get rid of the minus x at the bottom. And again, simplify this into x squared over concentration of the acid. Now, all we need to then do is rearrange and solve for x, and x is going to tell us the concentration of the hydronium ion, because that is what x equals, hydronium ion concentration. So if I rearrange this formula to solve for x, it's Ka times the concentration of the acid. Okay? So if we go through here, this is just, again, explaining how your Ka value formula can be written as hydronium ion squared, replacing the x for hydronium ion, over the concentration of the acid. So if you are asked to calculate for Ka, that's how you would solve for it. And then to rearrange for hydronium ion concentration, this is how you solve for the hydronium ion concentration when you have a weak acid. Okay, so it is not one of the top 6, or the Ka for weak acids are less than 1. All right, so for example, let's say we have acetic acid. So if I go back to that data booklet that I had up here, and I look up acetic acid is right here. This is the formula for acetic acid. This is the Ka value for acetic acid, 1.8 times 10 to the negative 5. So if we go back, again, in order to find the concentration of the hydronium ion, because it's a weak acid, I need to take that Ka, multiply by the concentration of the weak acid, and then square root it to get the hydronium ion concentration. Okay? So my Ka is 1.8 times 10 to the negative 5. This is the concentration of my acid. Acetic acid, again, is a weak acid. So when you have a weak acid, again, square root of Ka times the concentration of the acid gives you the hydronium ion concentration. Then to find the pH, take the negative log of this unrounded answer. Otherwise, your pH is going to be off. Okay? So if I go 1.8 times 10, sorry, my calculator. Okay. 1.8 times 10 to the negative 5 times 0.10, square root that answer, then take the negative log of that answer, exactly my calculator as it is. Actually hit the answer button, negative log of your answer. You get an answer of 2.87. Now, just a note, if the concentration was given as 0.100, I could still only have 2 decimal places in my answer because my Ka value only has 2 sig digs. So even though the concentration here has 3, the Ka is going to limit how many sig digs your answer can have. It is not a constant. It is a calculated value given in the data booklet. Okay? So again, there's only 2 total digits in the Ka, which means I need 2 decimal places in my pH. Let's look at another example. Same acid, we're just doing a different concentration of that acid. So our Ka is still the same. This is the concentration of the acid. Again, this is a weak acid. When I calculate the concentration of the hydronium ion, it's 1.8 times 10 to the negative 5 times 1 square rooted. And then again, to find the pH, I just need to take the negative log of that unrounded answer. So in your button, actually hit negative log answer, and you're going to get an answer of 2.37. Again, I have 2 digits in my Ka, 2 digits in my concentration, so I can have 2 sig digs in my pH, which are its decimal places. So 2.37 is the proper pH for this example. Now let's say you're given a question where it asks you to calculate the Ka. So remember the formula for Ka is it is the concentration of the hydronium ion, which was X squared, over the concentration of the acid. Now I am not given the hydronium ion, but I am given the pH. And remember, we can find concentration of hydronium ion by going 10 to the exponent negative pH. Okay? Now, when I get that answer, I am going to square it, because I need that squared, divided by the concentration of the acid, which is given up in the question, 0.25. So 10 to the exponent negative 3.48 squared, divided by 0.25. Now, for sig digs in my Ka value, it's not a pH value, so I'm not looking at decimal places, I'm looking at total digits. There are 2 total digits in my concentration and 2 sig digs in my pH, because what's significant in pH are my decimal places. So there's 2 sig digs in pH. I need 2 sig digs in my answer, and what is significant in Ka is total digits. Okay? Concentration, mass, volume, Ka, all those are total digits that are significant. It's only pH and pOH scale that the sig digs are only its decimal places. So if you're given pH, you look at its decimal places to figure out how many total digits you can keep in any other value other than pH and pOH. Okay? Now, there's also one other formula that we're going to look at in this video, and that is calculating percent ionization or percent reaction. So in order to find that, the formula is the concentration of hydronium ion divided by the concentration of the weak acid times 100. Because if it was a strong acid, this would be 100%. Okay? So for weak acids is usually when we're calculating it. So it's how much hydronium ion concentration there is compared to the weak acid, and then timesing by 100 to get a percentage. So let's say you're asked to find the percent ionization for a 0.5 mole per liter solution of hydrosulfuric acid if the hydrogen ion, now here's a note, hydrogen is synonymous to hydronium. It's just that hydrogen is forgetting the fact that in water, that hydrogen ion is not going to exist by itself. It's going to bond with the water to make hydronium. Okay, so hydrogen and hydronium can be used interchangeably. They mean the same thing. So to calculate my percent ionization, now again, it is the concentration of the hydronium ion, which is 5.0 times 10 to the negative 4, divided by the concentration of the acid, which is 0.5, and then times 100. Okay, so hydronium over acid times 100. So 5 times 10 to the negative 4 divided by 0.5 times 100. And I get an answer of 0.1. Sig digs, it looks like there's 3 and 2. The lower is 2. So that's 0.10 or 0.10% ionization for hydrosulfuric acid. All right. If we look at another example, you have a solution methanoic acid with a concentration of 0.1 mole per liter. You are given the pH. Anytime you're given pH, right away you're like, oh yeah, pH can tell me the concentration of the hydronium ion, 10 to the negative pH. So if I want to calculate, again, my percent ionization, when I go 10 to the negative 2.38, that answer is going to be my hydronium ion concentration. Now in this formula, the hydronium ion concentration is not squared. It's just hydronium over acid times 100. So 10 to the exponent negative 2.38 divided by 0.1 times 100. Again, I have 2 sig digs in my pH because the sig digs are decimal places. So I need 2 total digits in my percentage. So the answer would be 4.2% ionization. Now, before I end this video, here's a quick summary of all the formulas that we've looked at so far in terms of focusing on acids, okay? So again, if you have a strong acid, in order to find the concentration of hydronium ions, it is just the concentration of the acid. But if you have a weak acid, then you have to take the Ka, multiply it by the concentration of the weak acid, square root it, and then that will give you hydronium ions. Once you have the hydronium ions, you take the negative log to get the pH. Now again, if you're asked for Ka or percent ionization, those are a couple other formulas that, again, you're not given formulas, so you need to memorize them. All right? And that is it for this lesson. Thank you very much for watching.